Dear students, welcome back for the assignment number 10, the third assignment in the ordinary differential equations. So as you would have already received this, the first 6 problems will be discussed in your live sessions. So go prepared for the same. So in this video session, we are going to look at from the 7th problem. Okay, so what is the 7a? 7a is giving you a kth order linear differential operator. Okay, so the kth order linear differential operator, and we have to show that this kth order linear differential operator in fact defines a linear transformation from the vector space Ck, which is the set of all k times differentiable functions, okay, to the set of all continuous functions. Fine. So you would have already seen in your linear algebra course what is a linear transformation, that is a linear map, and what is a vector space, and so on, right? We have also used this during this differential equation course. So, and we have already seen in some previous assignment session when we did the first order ODEs, we had seen how a linear first order ODE is actually a linear map and so on, right? We had seen some properties. This is now in the kth order situation. Okay, so first of all, if you take this map, so what is L? So this L that is defined here, okay, this L that is defined here is actually this operator. So L acting, so okay, without even operator, if I can just say this L is this differential map. Let me not rewrite it. So this is, let's say, AK of x dk dx. There's kth order derivative, k minus 1 order derivative, and so on up to, let's say, a1 of x d by dx plus a0. Okay, this is your operator. So if L acts on y, it's precisely what you have here. It's precisely Ly acting on, where you just it just acts on y. Okay, so what is the question? So what is the question? A is asking, you can think of this differential operator that you have L as actually a map from Ck I bar to C of I bar, right? If you remember, what is Ck I bar? Ck I bar is the set of all map from I bar to R such that f is k times differentiable in the interval I. I closure, as we have said, is the closure, is the closed interval. So if, right, we have seen in the lectures, right, if I is your open interval A, B, where A and B can take infinity, but in that case the closed interval doesn't make sense. So the closure basically means, so the bar basically means it's a closed interval. So what is Ck of I? So for any k which can be a natural number, right? For any k, f is a map from I bar to R, which is all real valued. F is k times differentiable in I, and the kth derivative fk is continuous. In fact, all derivatives up to k is continuous, right? Because see, if f is k times differentiable, that means f prime exists. And if f prime, which means f is differentiable, if f is differentiable, then f is continuous. Now if f is double differentiable, then f prime is continuous. So up to k minus, so once I say it's k times differentiable, up to k minus 1, the continuity is already there automatically, right? And then the kth order is also imposed to be continuous. This is what is called Ck. The situation when k is 0, that is whatever is Ci bar, is precisely set of all map f from I bar to this such that f is continuous. This is Ci. So this question A is asking that this map L is a linear map. Okay, this map L is a linear map from Ck to Ci bar. Is that true? So what should you check for linear map? You have to verify that for every, so since these are functions, since they are real valued functions, we are going to these are vectors. So you can, we have already given it as an exercise in the lectures, that both, that is Ck bar, where you may even make k to be 0. K to 0 is precisely, so when you say k is 0, it is Ci. Okay, so when we say Ck bar, I can think of this as C0 as well, which is set of all continuous. This is, one can think of Ci as C0. So this is a vector space over the reals, because they are all real valued functions. Okay, so it's vector space over real. So what should you check to check that this L is a linear map? That for any alpha beta in R, you need to say that L of alpha of some element of Ck, let's say call it y1, and some other element y2, it should satisfy this property, that L of alpha Ly1 and beta Ly2. If this property is valid, this means that L is a linear map, right? So is this true, right? So we just have to verify that. So you have the definition of Ly, you plug it in there, and when you say linear ODE, this is precisely what you mean, right? So how do you check this? Wherever you have y, y here, y here, y here, all these y, you replace this, and then you see that this property that we are saying here, in fact for every k, d kx power k has this property. It's linear. Every derivative is a linear map for any k, right, or any I. So in fact I should not use k, it's not same as, so let's use I. Xi dixi. Okay. So because this property is valid, then in every place here they all will split like this, so this property is valid. So the first property is true, that L is a linear map is true from Ck to Ck for this operator. Okay. Now the 7b is telling you that if you take the kth order homogeneous equation, then the solution form a subspace in the space of continuous functions. Okay. Okay. So what is your so Ly? So basically, what we are saying is that if you define S to be set of all y in C of y bar such that L of y is 0. See, you should also observe this fact that Ck I bar is contained in C of I bar for all k, all natural numbers k, right? So when you say the domain of L is Ck, and the domain is actually contained in Ci as well, right? So if you look at S as the set of all solutions of this linear homogeneous equation, the question is to show that this S is a subspace of C. Will that be? So what should you check for subspace? First of all, 0 belongs to S. Is that true? Yes, that's true, because you take 0 function, you apply L of 0, it will be 0 because it's just derivatives of 0, which is 0. So this is obviously true. So 0 belongs to S. Now what should we check for subspace? If we take any two element U1 and U2 from S, we need to show that if U1 and U2 belongs to S and alpha, beta are, say, some real numbers, if it's a vector space over reals, then we need to check whether this is true, right? Now that's again, it's valid from the linearity of this, because what should you check? That for this to belong to S, L of this should be 0, right? So what is L of alpha U1 plus beta U2, which is by linearity L of U1 plus beta L of U2. But U1 and U2 belong to S, which means L of U1 and L of U2 is 0, which means it's alpha times 0 and beta times 0, which is 0, which means alpha 1 U1 is a solution, which means it belongs to S, which means S is a vector space over R, because alpha beta is coming from R. Okay, so the solution space is a subspace, is a vector subspace of the space of all continuous functions, the set of all continuous functions. So that's also we have shown. Now let's show C. What is C? C is saying, recall that we have stated a theorem that the dimension of NL is K, right? Use this information to give an expression for the general solution of this. So this is again, so here I use the notation S, but in fact if you notice in the lectures, we use the notation LL and NL, which is precisely N of L is what we used, which is a null space of the operator L, the S. So the S is precisely N of L. and we have just shown that n of L is vector. We have actually shown this in the lecture as well, that it's a subspace, right? Okay, so now what is C asking? So let's we will come to this question. Since there is no space, we will continue 7C here. We'll continue 7C here. Okay, so what is 7C? It's asking for the general solution of Ly, given the fact that the solution space, which is a subspace, is of dimension k. If you recall in the previous assignment, when we did the first order linear homogeneous situation, we had shown there that the solution space of the first order linear homogeneous ODE is one dimensional, right? And now here we have stated a theorem in the lecture that for kth order it's k dimensional. So if the solution space is k dimensional, what is the general solution? It's just so if NL is k dimension, right? That's the theorem. If NL is k dimension, then what happens is that NL will have a basis, right? So let's call y1, y2, and it will have k. So what is basis? This set is going to, so every element of NL is a linear combination of this k elements, can be written as a linear combination of these k elements, right? That's what it means, right? When you say it spans the thing. So every element can be obtained as a linear combination of these k elements. But what does general solution mean? How does any general solution of Ly equal to 0 look like? So if y is such that Ly equal to 0, you know that y belongs to NL. So asking for a general solution of Ly equal to 0 is same as asking, right? Is same as asking what is the general form of any element of NL. And if it's k dimensional, you know that any element of NL should be linear combination of these k basis elements. So that is how any general solution look like. So though there are infinite number of solutions for this problem, because it's k dimensional, it's enough to find k linearly independent solution to this problem. Once you have k linearly independent solution to this problem, you can write down any solution to that Ly equal to 0 problem, that is kth order linear homogeneous ODE, is a linear combination of the k elements. Okay, so that's about 7C. So we have written down the general solution. Now what about D? D is saying classify the set of all solutions of the inhomogeneous. So in C we had found the general solution of Ly equal to 0. What if the right hand side is not 0? It's a function f, it's a non-zero function f. Okay, so and that solution, so they say classify the solution in terms of the null space. You see, null space is the solution to this problem, which is different from this problem. This is Ly equal to f, this is Ly equal to 0. So what they're asking is, how do you write down the general solution of this problem if you know this problem? Basically in linear, right? So that's what D is. So 7D. So if you recall, null space of L is set of all y such that Ly equal to 0. Now question is, and we have already seen that any solution to y will be of this form, whatever we have here, right? Will be a linear combination of k elements. That's fine. Now let's look at the inhomogeneous problem f, where f is not the constant function 0, right? So here it's a constant function 0. So what happens to this inhomogeneous problem? What happens is this. So you see, suppose, let's say, sorry, right, suppose, let's say, yc belongs to NL, right? So any element of NL, let's say yc, which means that means what? That means L of yc is 0. I am using notation yc because this is what is called the complementary function that we will explain later. So just some element of the null space of L, and if it belongs to this set, it basically means that it's a solution to this homogeneous problem, right? If that is the case, you see that in this equation Ly, okay, I could add Lyc, and that will still be by linearity. It's Ly y plus c, right? And this is 0, so this is actually equal to Ly, and this was actually equal to f. So if y is a solution to f, then y plus c is also a solution to f for all y. If you don't know this notation, for all y c in null space. For instance, if yp is a solution to this problem, then Lyp plus Lyc, which is yp. So if yp solves Lyp equal to f, then yp plus yc solves, let's say, Ly equal to p, Ly equal to, if yp solves Ly equal to f, then yp plus yc also solves Ly equal to f for all yc in the null space, which means the number of solution to this is as many as the number of solution to the homogeneous equation Ly equal to 0. Right? It's as many as so whatever number of elements you have here, because for every choice of element from the set, you have a solution. In other words, the way if you imagine this in the sense of vector spaces, right, the solution set for this problem Ly equal to f is nothing but, it's just translation of this entire set. So all your solutions are coming from this set. Now this is a set, this is a function, this is like you are translating a set by a function. Okay, so this is that space, and that's what the 7D question was asking us. It was asking us that to classify the set of all solutions of the inhomogeneous in terms of the null space of L, and that's precisely this, that if so all solutions of this inhomogeneous problem is nothing but the translation of the null space of the operator of the linear map L, null space of the linear map L, by some solution of Ly. So if you just know one solution of this problem, call it yp, you know every other solution. Okay, so in other words, you see, life has become much simpler because NL was k dimensional. So for a kth order operator L, NL is k dimensional. So to know all elements of NL, you just need k elements. So you just need to know k elements. And once you know k elements, and if you know one solution of the inhomogeneous problem, you also know all the solutions of the inhomogeneous problem. And this is the property of the, and this is happening because the differential equation is linear. Okay, that's the advantage of this. Okay, now that completes 7D. Now let's come to problem number 8, which is here. Okay, what is problem number 8 saying? Problem number 8 saying find the curve y such that it satisfies this differential equation y double prime equal to y prime, and the curve is such that the line y equal to x is tangent at the origin. So let's do 8. So what is given is that we are given so let's call this is the y equal to x line. Okay, and we are being asked to find a curve maybe that's fine. Yeah, so let's call this the curve that we need to find. So what is the curve y? Okay, in addition, what is the property? That y satisfies this differential equation. Okay, so y, what is the curve which satisfies this differential equation, and which also has this property that at origin this line y equal to x is tangential. Okay, so now one can solve this using the differential equation technique. For instance, because y, so the unknown is y satisfies this differential equation y double prime minus y prime equal to 0. Now it has other information that at the origin it is tangent to y equal to x. So first of all, at the origin, what is the value, and if it's which means it intersects this line y equal to x at origin. So at origin the value of this line is 0. So the value of y at origin should be 0. Secondly, the tangential part of this y, so the tangent of this y evaluated at 0 should be 1, because the slope of the line, right, which has this the slope of this y equal to x line is 1, right? So that is the tangent which is tangential to the given curve. So in a sense, the y that we want to find should satisfy these set of equations, which is an second order initial value problem, right? So to find y, you have to solve this second order problem. So first you integrate this term here. Okay, so what you get when you integrate this term here, so you are going to get, if you integrate once, you are going to get let's say y prime minus y equal to c naught in first integration, but this is same as y prime by y plus c naught equal to 1. right? Now if you integrate that, this is nothing but log of y plus c naught, and that is integral is x, so you will get y plus c naught equal to exponential of x plus some constant. Let's write the constant as exponential as well, so you're getting at c1 of e power x, let's say, right? So that's the general solution, two parameter solution that you get, because you have a second order ODE, so you are getting a two parameter family of solution, right? And if you want to find y, you need to find c0 and c1, but then for that you have this initial conditions given, right, which is coming from the condition that was given, that y equal to x is tangential. Use that, so 0. So when you put x equal to 0 in this equation here, exponential of 0 is 0, so y of 0 plus c naught equal to c1 exponential of 0, which is 1, which is c1, and y of 0 is 0, so c, which gives you c naught. So the first condition gives you that c naught is c1. Okay. Now the second condition is going to give you y prime. So let's you differentiate this, right? So if you differentiate this, okay, we can even use this information here, right? We have this equation. So y prime of 0 minus y of 0, which is, so y prime of 0 is actually equal to c naught, which gives you c naught is 1, right? Which gives c naught is 1, which means c1 is also 1, which means your solution is y plus 1 equal to e power x, or in other words, y of x is e power x minus 1. Okay, so that's the solution to problem number 8. We have found the curve which has this property. Okay, so that settles problem number 8. Okay, now let's do problem number 9. Okay, what is problem number 9? What is given is a second order linear differential operator, and the coefficients p and q are continuous functions on R. Okay, what we need to show is the following. What we need to show, first A, that a solution to this homogeneous problem, linear homogeneous problem, second order linear homogeneous problem, with x-axis as tangent at some point must be identically 0. Right? This is something similar we have seen even in the previous assignment when we did first order. We said if a function vanishes at one point, then it should vanish everywhere, right? So here in A, what is being asked is that if you have right, if you have the curve y with which is, and let's say it's given in an interval I, so let's take the interval, let's take this as the interval I, let's say, and then we are given a point, some point, so say some point, right? So let's say this some point is some x naught, and at this point you are given this function which is where this x-axis is tangent to that solution. So the solution is such that okay, so the solution, so this is your y, suppose your y is this is your y, the solution yx, right? And what is y? It's a solution to the linear homogeneous problem, and it's such that at x naught that x-axis is tangent to the solution. Then, I mean, if basically this problem is telling you that this situation cannot happen, right? Okay, so basically this is telling you that this situation cannot happen. You cannot have a solution to this second order homogeneous problem which is vanishing at one point. Just, I mean, it is vanishing at one point here. So what is the how do you prove that? It's very simple, like we did before by the Picard's theorem. Y satisfies Ly equal to 0, and what is Ly? Ly is precisely y double prime plus px y prime plus qx y equal to 0. And then what you know is that since at x naught the value is going to be 0 because it's touching the x-axis, right? And then the derivative of y at x naught is same as the slope at x naught of that, which is also 0. So y prime is 0. So the y that you need to find, the y that satisfies this property here with x-axis as tangent at some point, should be a solution to this problem. And this is a second order initial value problem with the coefficients p and q being continuous. Right? If the coefficients p and q are continuous, then it satisfies the Picard's existence theorem, right? In fact, we not Picard's existence theorem. We are not, sorry, that was for the first order. We had given the lecture. So in the lecture, we had given the statement of, I mean, existence theorem for kth order linear ODE. So it satisfies those conditions where p and q are continuous. So and this will have a unique solution. But we already know y equal to 0 is a unique solution to this problem, right? So if you have a non-zero function satisfying this property, that's not possible, because then that gives you another solution to this problem. But this problem can have only a unique solution. So that function y has to be 0. So you cannot actually have a function with this property that we have given here. Okay, so that's about 9a. Okay, we have settled that. So any solution which has this property, the only solution that can have this property is the constant function 0. Okay, fine. Now b, what is b? B is saying if there are two solutions y1 and y2 of the linear homogeneous problem such that they have a common 0 at some point, then y1 and y2 are linearly dependent. What does this mean? What is it saying is that if you have okay, so we are given two solutions such that they have a common 0. So let's say this is solution y1, and let's say this is your solution y2, let's say, okay, and this is your point at which they have a common 0. Let's call it x0, for instance, right? So y1 and y2 are two solutions, and both of these are solutions to, so basically L of y1 is 0 and L of y2 is also 0. Both are solution to this problem. Then it means that then it should necessarily, so if this situation is happening, that means y1 and y2 has to be linearly dependent. That's the thing that we need to prove. Is this true? Okay, so let's that's very quick. If you, that's why we have this property of Wronskian, right? And once we have linear independence of function solution, Wronskian is the thing that we have introduced in the lecture. So we just have to verify that. So what we know about y1 and y2 is that both y1 at value of y1 at x0 is 0 and value of y2 at x0 is also 0. So what is Wronskian of y1 comma y2 evaluated at x0? That is y1 x0, y2 x0, y1 prime x0 and y2 prime x0. Now we don't know what is y1 prime, y2 prime, but that doesn't matter at all, because this, what we have here, this y1 and this y2 are 0, right? So which means that this is equal to this is 0. So this is saying that the Wronskian vanishes at point x0, and both y1 and y2 are solution to a differential equation. So you have y1, y2 as solutions to differential equation, and the Wronskian is 0 at a point, which means the solution has to be linearly independent. We had given this in the lectures, right? So they are two solutions. So both of them are solutions to the differential equation, and the Wronskian vanishes at a point. We have also seen that if the if they are solutions and if the Wronskian vanishes at a point, then it should vanish everywhere, right? So the Wronskian vanishes everywhere, which means the two functions are linearly dependent. Okay, now what is problem number C? Okay, let's do C. C is saying show that the solution, show that the function y1 equal to x and y2 sin x are not solutions of this linear homogeneous problem Ly equal to 0. That means these two cannot be solutions to Ly equal to 0. So y1 x is x. And as I mentioned earlier as well, that's the beauty of this mathematics, right? Here it's a general, so when you say Ly equal to 0, L is a very general operator in the sense that P and Q are not specifically given. P and Q are not given at all. So it could be any second order linear differential operator depending on the value of P and Q. Whatever is the value of P and Q, the C is telling you that x and sin x cannot be a solution to this problem. So we don't know the formula for y or anything, right? In spite of that, we can conclude that specific so these are specific functions, and this can never be solution to this, irrespective of what value you plug in. What P and Q continuous function that you plug in this differential equation, right? Now this is something which you can do on the in mathematics, right? And which is why this theory that we develop is very important, right? This is a much more general statement and result. Why is that true? From the previous result B, notice that y1 of 0 is 0 and y2 of 0 is 0. Suppose y1 and y2 are solutions to Ly equal to 0. If they are solution to this problem, then they have a common 0. And by the previous result, we should have that the function y1 equal to x and sine x both should be linearly dependent, right, from this B. But in the lectures, I have already shown in the lectures, we have already seen it in the lectures. If you have not, you can go ahead and do it. You can actually show that these two functions are actually linearly independent, which is a contradiction, right? We started with this assumption that suppose they are solution, then this should happen, that they should be linearly dependent, but they are actually linearly independent. That means our assumption that they are solutions to this homogeneous problem is wrong. So this is called proof by contradiction, right? What we have done here is that we had to show that they are not solutions. So we first assumed that they are solutions. So we assumed something that so we assumed exactly opposite to what we need. So what we need to prove. So we need to show that these two are not solutions. We assumed they are solutions, and in the process we obtained a statement which is contradicting a known fact, right? And why is that happening? Because our first assumption was wrong. Because we assumed something wrong, we ended up with a wrong conclusion. That's what it means. So which means our assumption is wrong, which means they cannot be solutions. Okay, so that's about problem number C. Now there is a problem number 9D, that is here. What is D? D is telling you that if you have two solutions y1 and y2 which are linearly independent of this homogeneous problem, second order homogeneous problem, then show that so D, we are doing D1, that between two consecutive 0 of y1 there is a unique 0 of y2. Okay, for instance, suppose say this is your, let's not go outside. Oh, okay, fine, I erased everything. Okay, suppose say this is your solution y1. Okay, and this has two consecutive zeros here. Let's call this x0 and let's call this point x1. So what we have, y1 of x0 is 0 and y1 of x1 is also 0. So these are two consecutive zeros of y1. Then there exists a unique 0 of y2. So y2 is another solution of linearly independent solution of this. So what should happen is that if this is your y2, then let's call this as your, let's say, x2. So there is a point x2, in between x0 and x1, and there's only exactly one point, there's a unique point x2 between x0 and x1, such that y2 of x2 is 0. Let's say this is y2. And that is what this is telling you. Again, I want to highlight here, L is a very general. P and Q is not given. P and Q are just continuous functions. It could be any continuous function. So L is a second order general linear differential equation. Whatever that equation is, the statement is that if you have two linearly independent solutions, then between two consecutive zeros of one solution, the other solution has a zero in between them. And this statement is actually, for instance, is also true. This is also vice versa, in the sense that I could replace the role of y1 and I can interchange the role of y1 and y2, right? Because if this is true for y1 and y2, and if y1 is linearly independent to y2, y2 is also linearly independent to y1. So between two consecutive zeros of y2, there will be a unique zero of y1. So the statement is true for both. So this is what we need to show. So you see, we can imagine about, though we don't know how how these solutions look like and so on. In spite of that, we can deduce these properties about the solutions, right? That's the beauty of doing this kind of analysis. Okay, now how do we prove this? Okay, now if, as we said, x1 and x0 and x1 are the zeros of y1, right? Of y1, then we can okay, how do I start? I want to show something, there is a zero of y2 in between. Okay, so we will do the same thing as we assume. So we will assume that y2 of x2, or not x2, because x2 is what we need to show, the existence of x2. Let's assume that y2 of x is greater than 0 for all x in this interval, right? So we need to show that y2 attains 0. Suppose, say, this does not happen, right? Which means that this y2, if there is no point x0 such that it is 0, which means it's either lying, it's all positive or it's all negative, right? So without loss of generality, let's assume it's all positive. Whatever whatever proof I'm going to give for kind of positive, you can do the same thing for negative also, starting from negative. Okay, so let's do for positive first. So let's assume, so suppose this does not happen, the same like proof of contradiction that I just mentioned some time back. We want to prove this. Let's say this does not happen, right? So which means that y2 has to be either positive or negative in this end for all points. It should be positive or negative for all points, because if there is one point, then this condition is satisfied. So for all points, it has to be non-zero, and if it's non-zero, it is, and it's a continuous function, so it has to be, if it's non-zero at x0, then up to x1 it has to be, if it's positive at x0, it has to be positive up to x1, right? Understand what I'm saying is, right? If it is not coming down to 0, and if it's positive, it has to be positive throughout up to x1. If it has to change sign, it has to go through 0, because they are solutions to differential equation which are continuous functions. So it has to be positive in the entire interval, or negative. Okay, whichever one of these will happen. Okay. Okay, now we will also observe that y1 prime is not equal to 0. Y1 prime at x0, that is the slope of this curve at x0 and x1, is not equal to 0. And why is that? Suppose this was equal to 0, what would happen is that y1 would be solution to this initial value problem. Suppose, say, this was 0. Okay, this was 0, then that y1 would be solution to this problem, and by uniqueness we know if y1 is a solution to this problem, then y1 has to be necessarily 0, right? And that's not the situation we are in, because we are saying that they have two consecutive zeros, x0 and x1, which means they are non-zero between x0 and x1. So it's a non-zero function. So if that has to happen, then both y1 prime at x0 and y1 prime at x1 both should be non-zero. That's what we have said here. Okay, so this is a property that we know from what is given. This is what we are assuming. This is our assumption, or what's usually called unsars, or whatever. But anyway, it's not even unsars. This is just a proof by contradiction for wrong assumption. But you can see it. Okay, so y2's prime is let's say it's either positive or negative, whichever is, fix one of them. So now what happens? So if y1 prime of x0 is non-zero at this, that is at this point and this point, the slope is non-zero. That means the slope is either positive or negative, right? Because there are only two possible situations. The tangent is positive and negative, or the opposite sign. So the picture that is shown here, y1 prime of x0 is positive and y1 prime of x0 is negative, right? But you could also have, if they have consecutive zeros, it could also go below the x-axis, right? That could also be a graph of. So another possibility is y1 prime of x0 is negative, and then this should be x1. Okay, so these are the two possibilities, right? So now let's go ahead and see what happens. Now what is given to us, that they are linearly independent solutions, right? So what is Wronskian of y1 y2 at the point x0, right, which is y1 x0 y2 x0 y1 prime x0 y2 prime x0. Okay, now y1 x0 is 0, y2 x0 is something which we don't know, right? And y1 prime x0 is non-zero. We have concluded that. So whatever this is 0, right? You agree, right? This is 0 because of this assumption here. So what we have is minus, so the Wronskian is minus y2 of x0 y1 prime of x0, right? But y1 prime of x0 is, let's say, positive, right? So in this situation it's positive, and y2 of x0 is also positive, right? So in that case this is negative. Similarly, if you compute Wronskian of y1 y2 at x1, that will be equal to, right, the same thing with y at x1. You will have minus, because at x1 again y1 x1 is 0, so what you will get is the value of y2 at x1 and y1 prime at x1. And in this case again y2 of x1 is positive, right? y2 of x1 is positive, and y1 prime of x1 is positive from here. This one. Because earlier we took this one, so we need to take the corresponding situation. y1 prime of x1 is negative, so this is negative, this is positive, right, which means it's negative, so this is positive. That means Wronskian at x0 is negative and Wronskian at x1 is positive. If you change this situation and take this situation here, you are going to get the other situation, that in the equivalent situation you are going to get this is positive and this is negative in this situation. Oh my goodness. So this was y1 prime and this is also y1 prime, and if you take the second situation, what you obtain is what is written here in the red, right? But in both cases, so whatever situation you take, what you know is that the Wronskian changes signs at x0 and x1, which means that the Wronskian has to be 0 in some in between point. So there exists an x between in x0 and x1 such that Wronskian of y1, y2 evaluated at, let's call it x2 then, some x2, such that Wronskian of y1 and y2 evaluated at, so there is some point x2 such in between where this should vanish, right, because they have opposite signs. Let's not call x2 because I've already used x2 here, right? Let's call something else. What do we call? Let's call, what do I call? Just call x3, okay? I can't think further. Fine. So, okay, so there is an x3 such that this Wronskian becomes 0. But we know that if Wronskian is vanishing at one point for linearly independent solutions, right, then the Wronskian has to be 0 everywhere. If the Wronskian is vanishing at one point, then it's 0 everywhere, which means that the solutions are linearly dependent, but the solution is given to be linearly independent. That is what is given to us here. They are linearly independent solutions, so they cannot be linearly dependent, which means the Wronskian cannot be 0. So this conclusion that we have obtained is wrong. And why did we obtain this wrong conclusion? Because we started with a wrong assumption, right? The same thing will go ahead if you even start with negative, right? So finally what you have shown is that this statement is wrong, that your assumption that you have made, and if this statement is wrong, that means there is some point x2 such that y2 x2 is 0. Okay, but we still have not finished the proof. We have only shown the existence. We still have not shown the uniqueness part, that there is only a unique point for which this happens. But that's again easy, because once we have shown the existence, so just imagine this, we have shown the existence, so between two consecutive points, so let me choose some, between two consecutive points, how come I have used all the colors? Okay, between two consecutive points, if there is a 0 x0, and let's say there are more than one 0, which means this function is not actually going here but is coming here and going and taking a turn here and taking another 0 here. Suppose this function has more than one 0 between these consecutive zeros, and since these two solutions are linearly independent, this function should have its 0 in between these two consecutive zeros. And if that's true, then that contradicts the fact that these 2 points are consecutive zeros, because now you have introduced another 0 between these two consecutive zeros, which means that there cannot be another 0, right? That's a proof which I have explained, right? So y1 of x0 is 0 and y1 of x1 is also 0, and what we have shown is that there is an x2 which is 0. Suppose there exists an x3 between x0 and x1 such that y2 of x3 is 0, then x2 and x3 are consecutive zeros of y2. That means there exists an x4 between x2 and x3 such that y1 of x4 is 0. But if x4 is between x2 and x3 and x2 and x3 are between 0 and 1, this x4 is actually belonging to x0 and x1. But x1, 0 and x1 were consecutive zeros, but x4 is also a 0. That cannot happen. That is because this cannot happen. So I have shown you the proof both pictorially and also by writing. Okay. So go ahead and if you have not understood, watch carefully, can write it properly and so on. Okay. Anyway, I spent too much time on it. Okay, there is one more statement. This is taking too long. Okay. Now let's do this proof in the next page. Okay, let's do it here. And we will continue the next problem on the next page. So this is 9D2. What is the 9D2 statement? It's telling you that if you take two different linear combinations of linearly independent solutions, then they are if you take two different linear combinations of this linear independent solution here, then they themselves are linearly independent solution of the homogeneous equation as long as AD minus BC is non-zero. Okay. So how do you prove that? So you are given first y1, y2 are linearly independent solution of Ly equal to 0. What you are being asked to show is that if you take a linear combination, it is given to be it is given to be ay1 plus by2. Let's call this the function u1, let's say, or let's know, why do you need 1? You just call it u. Okay, call this function u1. What we are asked to prove is that this function, and let's call this other function the other linear combination. So you take this linear combination of y1 and y2, let's call that u and v. Then what we need to show is that u and v are linearly independent solution of Ly equal to 0 if and only if AD minus BC is not equal to 0. So how do you check whether two solutions are linearly independent? Naturally, look at their Wronskian. So let's look at the Wronskian of u and v. and that is going to, once we compute that, that's going to tell us whether it's linearly independent solution or not, right? Now when you write Wronskian, what you get is this. It's AY1 BY2 and CY1 plus DY2, and then AY1 prime, BY2 prime, CY1 prime, and DY2 prime. Okay, so we have this. Now what we can do is try computing these determinant. So what we have is A C Y1 Y1 prime, A D Y1 Y2 prime, B C Y1 prime Y2, B D Y2 Y2 prime minus A C Y1 Y1 prime minus AD Y1 prime Y2 minus BC Y2 prime Y1 minus BD Y2 prime Y2. Now you see that this goes off. What else goes off? Y1 prime Y2. So okay, what else goes off? Y2 prime. These two go off, right? And what remains is the remaining stuff, which is, you can see if I combine this Y1 Y2 prime and something am I missing? This one. If I combine them, what I get is AD minus BC Y1 Y2 prime, and then if I combine these two with a minus sign, let's say, then what do we get is AD minus BC Y2 Y1 prime. This, if you notice, is nothing but AD minus BC Wronskian of Y1 Y2, right? Because Y1 Y2 prime minus Y2 Y1 prime is Wronskian of this. So Wronskian of UV is AD minus BC Wronskian of this. So if the function has to be linearly, if this U and V has to be linearly independent solutions, that means the Wronskian WV prime has to be non-zero, right? But Y and Y1, Y2 are already given to be linearly independent, so this Wronskian is anyway non-zero. So if this has to be non-zero, then this has to be non-zero, which is precisely this statement. Okay, so we are done. And this is vice versa, this is right, so we actually proved both ways. If this is non-zero, this has to be non-zero. If this is non-zero, this has to be non-zero, which means linearly independence of U and V. Okay, now let's go ahead and let's do problem number 10. What is problem number 10? We are given two functions y1 and y2, and we need to show that if the Wronskian is non-zero, then there exists a unique pair of continuous functions p and q such that y1 and y2 span the solution space of the second order problem. Okay, so if the Ron, so basically here it's more or less the other way. What is being given is two function. Now you need to find the P and Q such that this y1 and y2 generate the solution space, because it's a second order equation, so and it's a homogeneous equation. So for second order equation, the null space is two dimensions, so you need two functions to generate the solutions, and that's what we are. So we need to, so here given any two functions, question is, can you always find a P and Q, any two function which are such that the Wronskian is non-zero, basically some kind of linear independence is what we are imposing there. So if the Wronskian is non-zero, then you can always find coefficients such that y1 and y2 are solutions to the ODE corresponding to those coefficients. That is what 10a is. Okay, so let's do 10a. So can we find the P and Q? So what are we looking for? We are looking for P and Q such that the given functions y1 and y2 are solution. So basically L1y is equal to 0 and L1y2 is also equal to 0. But you know what is L1y and L2y, which is y1 prime px. So we need to find P and Q like this. So for which P and Q will this be valid? Okay. So this is like system of equations, right? If you want to solve for P and Q, y1 and y2 are given, you just have to solve for them. So if you, for instance, one can multiply this equation by say y2 and this equation by y1, then what you have is you get y2 here, you get y2 here, you get y2 here, you get y1 here, you get y1 here, and you get y1 here. And if you subtract them, basically this and this goes off, and what you will remain is something in terms of P. So what you will get is P times the Wronskian of y1 comma y2 equal to y2 y1 prime minus y1 double prime, right? Because y2 y1 double prime and y2 y1 double prime minus y1 y2 double prime. This is the first equation, and whatever you have here is precisely the Wronskian, right? So you actually have the formula pxq is y2 y1 prime y1 y2 prime by Wronskian, and this because y1 and y2 and we are given that this Wronskian is non-zero, so you can divide by the Wronskian, right? In fact, you can observe that this is nothing but minus Wronskian of y1 prime and not y1 prime, I'm sorry, minus Wronskian of y1 y2 prime of that. So this is the derivative of the Wronskian divided by the Wronskian. You do the same things to find. Now we have found P. We need to find P and Q. We have found P. So now you do the same thing. What you do is, in the same equation, you could have the same equation, instead of this, you could have multiplied y2 prime and y1 prime. In that case, you would cancel out the term here, you will get an expression in terms of q. So if you do that, you are going to get y1 prime, y2 double prime, y2 prime, y1 double prime by Wronskian of y1 comma y2. This is what you will get for q. So you have p and q found. In fact, there is also another way, in the sense that once you find a p, you can always find q by substituting p here and writing q in terms of every other thing. And in that case, you will have to get the same expression for q because they satisfy this condition, right? Yeah, that is one way. The other way is that you can also write it in terms of this Wronskian. Both are fine. Okay, so we have found p and q, and if you use this p and q in this operator L, then the given y1 and y2 will be solution to that, because that is how we derived it. So that's 10a. Now 10b is precisely some examples where you need to check this thing. So if you are given these solutions, find the second order linear ODE such that these are pairs of solutions. So you are given y1 and y2, find the corresponding p and q. Okay, so let's quickly do this. It's taking too much time, so let's quickly finish it off. So bi, so you are given e power minus x and x power e power minus x. You just have to use the formula, right? But I just want to, so you are given these two functions. We already have p and q. So for that, to use p and the formula for p and q, we have to find the Wronskian. So in this case, the Wronskian, if you for these two functions, if you use y1 as this is as your y1 and this as your y2, you are going to get the Wronskian to be e power minus 2x. Okay, and once you use w to be that, and you use that in this formula here for p, you are going to get p is 2, and you are going to get q to be 1, which means your differential equation that you are looking for is y double prime 2y prime of y equal to 0. This is the differential equation for which these two will be solutions. Okay, and there are also other ways of doing this, but that depends on each kind of problem type that you can even guess by looking at certain equation. For instance, in this case, if these two have to be the linearly independent solution which spans a second order ODE, and if you look at these functions e power x, so you look at its linear combination. So if you look at alpha y1 and beta y2, what you see, it's alpha e power minus x plus beta x e power minus x, which basically is alpha beta x e power minus x, right? This is what you get. And now if this linear combination, if you call yx, then what we have obtained is yx is equal to alpha x beta, and this e power x can be brought in here. So the solution, any linear combination of the given function will be of this form. So if you want to know the differential equation for which this two parameter family is a solution, you just have to eliminate the parameters, right? So you differentiate it with respect to the x variable. So you get e power x y prime plus y by product rule, and then you get beta. If you differentiate it once more, you get e power, again by product rule, you get 2y prime plus y equal to 0. This is always non-zero, So this has to be 0, which is precisely this. Okay, so that's another way of finding the differential equation. Right, and in this case it's here. There's also one more way, but little more clever way, is that if you look at these two functions, they are linearly, this is e power x, but a polynomial multiplied, so they are linearly independent, of course. Now the other point is that what are these so this technique usually works only if your corresponding differential equation is with constant coefficients, which we don't know a priori, but you can make a guess. So look at these two, what are the roots of that, so what are the roots of the characteristic equation which will give you these solutions, right? So this you can actually see is repeated, only for repeated root you get this multiplied by polynomial, right? So it is actually root minus 1. So if you look for the characteristic equation m equal to minus 1, what is that root? So it's basically, and m is a repeated root, so it's m plus 1 whole square equal to 0. So what is the equation which has this as its characteristic equation? What is this equation? M square 2m plus 1 equal to 0. So what is the ODE which has this as the characteristic equation? This one. So you have this solution. Okay. So that is another way of obtaining the solution, but that is kind of some kind of clever or guesswork, that looking at these functions, you know that they are linearly independent. So these type of functions come only by as roots of characteristic equation. It has to be m equal to, so it's essentially minus 1 as a repeated root or double root, right? And then from that you can make a guess like this. Okay, that's for B1. Let's look at B2, e power minus sine 2x and e power minus x sine 2x, e power minus x cos 2x. Okay, I think I'll just leave it for you to as an exercise. If you take those two functions, first technique is that you can compute the Wronskian, the whatever formula we had. And just for you to check, I'm just giving you. So if you compute the Wronskian, you should get minus 2 e power minus 2x. Use that in the formula for p, you should get p to be 2, and use that in the formula for q, you should get q to be 5. So the OD that you will get is y prime 2 2y prime plus 5y equal to 0. Okay, so that's your OD that you will get. The alternate way is to look at these two functions, e power minus x sine 2x, e power minus x cos 2x, right? Then you look at its linear combinations, alpha times plus beta times. Call this as your yx, right? So what you are getting is alpha sine 2x beta cos 2x y e power x. You eliminate the constants, because right, if you eliminate the constant, whatever differential equation you get is the thing. There are two constants. So if you eliminate the constant, so for that you differentiate twice. If you differentiate twice, what you get is minus 4 times alpha cos 2x plus beta sine 2x times e power x y double prime 2y prime plus y. But this alpha 2x beta 2x is precisely y e power x. So it's minus 4y e power x. So that's going to give you e power x y double prime 2y prime plus 5y equal to 0. This is non-zero, which means this has to be 0. That's the differential equation that you get. The other technique, as I said, because this turns out to be a constant coefficient ODE, in any case, if you look at these two functions, you know that they come as roots of the complex number minus 1 plus or minus 2y. So if you look at m equal to minus 1 plus or minus 2y, this what is the characteristic equation for which these are the roots, which comes from m plus 1 plus 2y, m plus 1 minus 2y equal to 0. So if you use that, you see m plus 1 whole square plus 4 equal to 0, which is m square plus 2m plus 5 equal to 0. So the ODE for which that is a characteristic equation is precisely what we had obtained. Okay, finally the last problem, which is 3x and x squared plus 1. Okay, so in the first two examples, both turned out to be constant coefficient ODE. So let's give an example of x and x squared plus 1. So these two functions, what happens? So let's compute the Wronskian of these two. You can also write like this. I'm just being a bit lazy and not writing like this. Otherwise, since the functions are given, you should write Wronskian like this. Okay. So Wronskian of x square plus 1, if you compute it, you will get its x square minus 1. Up to now, all the Wronskian that we computed were some constants which were independent of the function. Now we are getting something. So now, is this non-zero? This is not always non-zero, right? It is non-zero only for x not equal to plus or minus 1. So if you ignore in your domain these 2 points, if your domain does not contain, so any interval not containing these 2 points, you can for that this is non-zero, and then you can use for those intervals you can find p. You will get 2x minus 1 minus x square. You can also find q. You will get minus 2 1 minus x square. Okay, and using, so now that you have this, so the ODE that you get is 1 minus x square double prime plus 2xy prime minus 2y equal to 0. Okay, so that's your ODE. You can also obtain, you cannot use this third technique that we used here by looking at the characteristic equation. That method will not work here. In any case, you don't know what roots will give you this, right there. What you can do is the elimination of parameter method, and that for that you need to take the linear combination, right? We take this linear combination, then you have to eliminate the parameters. So you have to differentiate. If you differentiate once, what you will get is alpha plus 2 beta x, and if you differentiate once more, you get y double prime to be 2 beta. So now you use this information to eliminate. So y prime is alpha plus x y double prime. Okay, so that gives you alpha is x y double prime minus xy double prime plus y prime. That's your alpha and beta. So your y will be minus x square double prime plus xy prime, and then y prime by 2 x square y prime by 2 plus y prime by 2, right? So that we can okay, so that gives you, let's simplify that, we should get the same. So here there is minus 1 and plus half, so half minus 1 will give you minus half. So what you have is minus x square by 2 plus 1 by 2 of y double prime plus x y prime, which is 1 minus x square of double prime plus 2xy prime minus 2y equal to 0. Okay, so that kind of completes this assignment. Anyway, I hope that has helped you, and if you are, please go ahead and try doing it, see it again to understand any further. With this, we'll stop here. I'll see you in the next assignment. Thanks a lot.